I will. Oh, so probably. Okay, rational functions. So as I said the other day, think of a rational function as being a fraction. The difference being the denominator has to in itself be a function. So I have to have a variable in the denominator's position. I can have a constant on the top for the numerator. The denominator has to be a function. So it says the degree of the denominator needs to be greater than 0, or it's simply a polynomial function. In other words, if I had x plus 7 over 3, yeah, it looks like a fraction, but it's not, because I can rewrite this as 1/3 times x plus 7. There is no variable in the denominator. So that's the first thing, is to be able to recognize what a rational function looks like. So a rational function, denominator with a variable. What that means, denominators cannot equal 0. So if I have a variable in the denominator's position, I have to look at whether or not there are circumstances where a value of x could make the denominator equal to 0. And if there is, I'm going to have something that's called discontinuity, or a non-permissible value. So if the denominator can be made equal to 0, then the value of that variable is called a non-permissible value. So for example, in this function right here, if x is equal to 1, I get 1 minus 1 is 0. That becomes a non-permissible value. So I would actually say, in this case, you'll see a lot of the equations. If I was to write this out, I would actually beside it write x cannot equal 1. That becomes kind of my restriction to the function. So that tells me that x could be all these other things, but x can't be equal to 1. In this equation, if I let x squared minus 9, and I figure out what values will make that equation equal to 0, I get a positive and a negative 3. So again, I would write down x can't equal those values. As long as it's any other number, I'm going to be able to find a value for f of x, or g of x, I guess, in this case. So h of x, what would be a non-permissible value of h of x?
-2.
-2. So x cannot equal -2. So that's an important thing to realize, is that there are non-permissible values, things that x might not be able to be. Okay? There's not always a lot, or sorry, there's not usually a lot of non-permissible values, but they are there. So I'm going to let you continue reading on the rest of the page, because there's 2 types of discontinuities to look at. So with our discontinuities, there is an example here of a function that there are no non-permissibles. X squared plus 1, you're always going to get a value, no matter what x is. If x is 0, I get 1. If x is positive, I just get 1 more. When x is negative, when I square it, I get a positive. So this would be an example of a rational function where there are no non-permissible values. So hint, anything that's squared plus a value. So x squared itself is going to have a non-permissible, but the minute I add a value to it, everything's going to be positive. I'm never going to get a 0. If a rational function has a non-permissible value, then the graph is not continuous. There's going to be a break in the graph where that non-permissible value is. There's 2 types of breaks in the graph. There can be an asymptote. This is called an infinite discontinuity. So what it means is that the graph gets close to that breaking point without ever crossing over. It just keeps getting closer and closer and closer to it. Then there's what we call point discontinuity. And that's where there's an actual gap in the graph. So it's not that the graph leads up to this breaking point, it just goes along and kind of jumps over that point and keeps going. So it's shown as being a hole on the graph. So what we're going to look at in this class is infinite discontinuities. In other words, asymptotes. So if we look at the following example, a rational function, f of x equals x minus 1. Since division by 0 is not this function would be what?
1.
1. So it says complete the table of values below, plot the points on the grid, but don't connect them at this time. So if x equals -5, I get 1 over -5 minus 1, which is -6. So I get -1/6. When x equals -2, I'm going to get, what will I get? -3, so I'll get -1/3. When x equals -1, what will I get? -1/2. When x equals 0, I will get -1. When x equals 1, undefined. So I'll get this not defined value. And then when x equals 2, what will the function equal? And then when it's 3, I would get 1/2. When it's 4, I get 1/3. And when it's 5, I get not 1/6, 1/4. So what we're going to do is we're going to investigate the behavior of this rational function as I get closer to this non-permissible value of 1. So instead of just looking at 0 and 2, we're looking at things like 0.5, 0.9, 0.99, and etc. So if x equals 0.5, and if I want to use my calculator to help me with this, so I would have 1 divided by, open bracket, 0.5 minus 1. And so I want to put that in brackets so that the calculator knows that calculation happens first, and then I divide by that, 1 divided by that answer. So I get -2. And if I go second entry, it retypes it because I don't want to have to type it all over again. I can change the 0.5 to a 0.9, and I get -10. So if x equals 0.5, I get -2. Then I get -10. If I change this to 0.99, I get -100. So I'm getting larger values. And then when x equals 1, I've got that not defined happening again. And then I'm going to give you a couple of moments, and what I want you to do is I want you to do the next 3. So if x equals 1.01, what is the value of f of x?
100.
100. And when it's 1.1, the value is?
10.
And when it's 1.5, the value is 2. So now if what we want to do is we want to plot the points on the grid and join the points with a smooth curve. So when x equals -5, I get a value that's like -1/6. So it's going to be a small value. When x is -2, I get -1/3. So -1/3, third of the way down. When x equals -1, I get -1/2. When x equals 0, I get -1. When x equals +0.5, so halfway in between, I'm at -2. And when it's at 0.9, I'm at -10. So if I notice these points, the smooth curve that I get looks like this. It's hugging the x-axis, and then it comes through. And what line does it seem to hug going down? What line am I hugging? I'm hugging this line that goes through 1. If I look at the grid marker, it's not going over it, it's just hugging it. And I can see that by the values, because when I'm at 0.99, I'm at a -100. Then if I look at the rest of my scale, when x equals 1.01, I'm at positive 100, which I can't graph. At 1.1, I'm at 10. At 1.5, I'm at 2. And then at 2, I'm at 1. At 3, I'm at 1/2. At 4, I'm at 1/3. And at 5, I'm at 1/4. So this time, if I join this smooth curve, I get this line, or this curve. So when we're drawing these, what I get is I get this imaginary boundary that this graph has gotten closer to, but it hasn't gone over it. So sometimes we draw that imaginary boundary like this. We put it as a series of, or as a dotted line. I'm going to make it red so it stands out. That is my asymptote. That dotted line is that vertical, it's that boundary point that the graph does not cross over. Do you see another boundary point that the graph does not seem to go over? The x-axis also acts as one. So it's a horizontal boundary point. So question E says, describe what happens to, or sorry, verify using a graphing calculator. So if I was to put this into my calculator, my window settings, if I follow what's on the board, it looks like it's going from -7 to +7, and then from -10 to +10. So when I put in my y1, I clear what I have there. So this is 1 divided by bracket x minus 1. Now, depending on the configurations of your calculator, this is what some of your calculators might do. Some of your calculators might just draw it like this, and some of them, when they're drawing it, you'll get this pattern that'll go like this, and then all of a sudden this like mark or slash will come down, and then you'll see this. So in those cases, the calculator has drawn an asymptote, but that asymptote is not actually part of the graph. It's an imaginary boundary line. So that's why we're drawing it in with dotted lines, to show that it's not part of the function itself. It's a characteristic of the function. So if we describe what happens to the value of the function as x gets more and more positive. So as we go along here in my domain, what is happening to the function? What is it getting closer and closer to? The x-axis, which is the value of, what's the y value? 0. So it's getting closer to 0. So as x is approaching infinity, f of x is getting closer to 0. As I get more negative, as my x values get more negative, what happens to the graph? What happens to the value of the function? So what is this line approaching? 0 as well. So it's also getting closer to 0. So then G and H say from the options in the curly brackets, circle the correct alternative. So as x gets closer and closer to that non-permissible value of 1 from the left-hand side, so this is my left-hand side, as I get closer and closer to this negative infinity. And as I approach it from the right-hand side, as I get closer and closer to this boundary line on the right, am I closer to positive infinity or negative infinity? Positive infinity. We have negative and we have positive. So at the top of the next page is just some more explanations as to what is an asymptote. So a line that a curve approaches more and more closely without crossing or without actually reaching is called an asymptote. With reference to the exploration on the previous page, as x gets closer and closer to the value of 1, the graph gets closer and closer to the equation of the line x equals 1, but never actually reaches it. So it'll always be 1.0000000000000 something, or 0.9999999999999 something. So it never actually equals 1.0. Okay? This is called a vertical asymptote, and it occurs because 1 is a 0 of the denominator. So my vertical asymptotes come as a result of my non-permissible value. If you have a non-permissible value, you're going to either have this whole or you're going to have this asymptote. As the absolute value increases, or of x increases in value, the graph gets closer and closer to the x-axis, that line of y equals 0, but never actually reaches or crosses the x-axis. This is called a horizontal asymptote. Horizontal asymptotes are not part of infinite discontinuity. Infinite discontinuity is the vertical asymptote. So if you have a what it means is if you have a non-permissible value, you either have this line, this asymptote line, or a hole. The horizontal asymptote does not necessarily happen with every case, and we'll examine horizontal asymptotes as we go through. Because there are circumstances where sometimes you have one, and sometimes you don't. Vertical and horizontal asymptotes are represented with dashed lines, but they're not part of the graph. And that's what I was saying before. They're not part of the function of the graph. They're simply a characteristic, something to look for. So consider the function f of x equals 3 over x. What is the domain of this function? So are there x values that I cannot have? Or could x be anything?
It can't be 0.
X cannot be equal to 0. So the domain would be the set of x values such that x cannot equal 0, but it could be anything else. So it says use a graphing calculator to sketch the function, to graph the function, but don't sketch the function. So this almost looks like it's a standard grid. So y equals 3 divided by x, and I could go zoom 6 to get that standard grid setting, and there's my graph. What is the equation of the vertical asymptote? Where do you think that vertical asymptote occurs? When x is equal to 0. Non-permissible value becomes the asymptote. So it says, show the vertical asymptote on the grid by drawing a dashed line. So there's my vertical asymptote. So then when I graph this, what you'll notice is I get this graph. As I get closer to 0, the function gets closer to negative or positive infinity. And as my x values get larger, those y values get closer to 0. So I get two curves that look like this. draw those showing that the curves are getting close to the asymptote without crossing the asymptote. What's the horizontal asymptote? The x-axis. How would I write that as an equation? Y equals 0. So what's the range of this function? What are my possible y values? Can y be anything? Anything but 0. So the set of y values such that y cannot equal 0. Okay, next equation. 2x over x plus 1. Are there non-permissible values? Are there values that x cannot be? -1. So that gets part of my domain. X cannot equal -1, but it could be anything else. So what I want you to do is I want you to graph this and then go through the next 5, 6 questions. Okay, if we use a graphing calculator to graph the function but we don't sketch it, using what you got on the graphing calculator and what you got from question A, what's the vertical asymptote? X equals -1. So if we draw that using our dashed line, x equals -1, there's my line. Then it says estimate the equation of the horizontal asymptote, because this time it's not approaching this line here. What did it look like it was approaching? What line is it actually approaching?
Looks like it's approaching 2.
Approaching 2?
Y equals 2.
Y equals 2. So it looks like it's approaching this line here. And you can verify it by using your table of values feature. So what you could do with your equation, so I have y equals clear bracket 2x bracket and then x plus 1. And then I can go to my table set and turn my table set to ask. And then when I go to my table, oh, I guess maybe I should press enter on ask first. There we go. Then I can put in those values, such as when x equals 100, y equals 1.98. When x equals 1,000, 1.998. When x equals 10,000, etc. I get 1.99. So it is showing that, yes, it is actually approaching this value of 2. As the value of x gets really, really large. As the value of x gets really, really small, such as -1,000, I get 2.02. So it's a little bit over 2 this time. So then when I go to sketch this, what I get is this graph that on this side goes like this. And then on the other side, remember as the value of x got larger, I approached 2 from the bottom. And when x equals 0, I get 0 over 1, which I can have. So when x equals 0, y equals 0, so there's an intersection point. And there's my other graph. So we've got that y equals 2 as my horizontal asymptote, which then means that my range would be the set of y values such that y can't equal 2, but it can equal anything else. So this is an example of an equation where the horizontal asymptote is. So we've seen an example where we have the x-axis as an asymptote, where we have the x-axis as not being an asymptote. So if we look at this third one, the function x squared over x minus 2. If I go to graph first of all, vertical asymptote. 2. That would be my vertical asymptote, and we're going to draw it. So I now have that drawn into place. Then when I go to graph this, x squared divided by bracket x minus 2. What do you notice this time? Do I have a horizontal asymptote? No, I have a whole big field. I don't have a fence that I can't cross. I have like a whole field I can't cross. So it's kind of like the, I can't even think, the zone between North and South Korea, where like the minefields are. It's not just the border, it's like a range that you cannot cross into. So that's what we're looking at in this case. So my graph does look a little bit different this time. I have this part of the graph that it kind of goes in a curve. So it's not really approaching, it's kind of just approaching the vertical asymptote, but it's not approaching a horizontal. And the same thing up here. I get this graph that approaches on this side and then curves and goes up in the other direction. So do I have a horizontal asymptote? No. So if I wanted to calculate the domain and the range, well, we know what the domain is. X can't equal 0. Or sorry, not 0. X can't equal 2, because then it would equal 0. The range is a little bit harder to get. So in order to get the range, what I would want to do is I'd want to know what my local, we call them local mins and max. Local because this right here is not a minimum point, nor is it a maximum point. But it is kind of the maximum for this part of the graph. This is the minimum for this part of the graph. So I can calculate that. Second calc, I want to find the maximum, which is 4. So, oops. So left bound, right bound, and I get this value that's really, it's 0, because negative 4.22 times 10 to the negative 12, that's 0. Then if I find the local min, what I have to do, look at where my cursor is. So I'm going to keep my cursor going to the right. It's going to disappear from my screen, and then it's going to pop up. If I look right here, it's gone over the 2 value, and it's at y is equal to 35. And now I can see it just barely starting at the top of my screen. Enter, 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 and I get 8. So when I write this out, my range would be to set a y value such that y has to be either less than 0. Can it equal 0? Yep. Or y has to be greater than or equal to 8. And it is important that we use the word or, not and, because it can't be less than 0 and greater than 8 at the same time. It's only one or the other. Okay? So in the previous investigation, the horizontal asymptote will fall into one of 3 categories. Either you're not going to have one, or it's going to be the x-axis, or it's going to be a line that's parallel to the x-axis. So y equals k. That was the second one. We are going to actually look at how I can calculate those, how I can determine those without depending on a graphing calculator. Graphing calculator has some limitations when graphing some rational functions. These suggestions can give you a clearer representation if you need them. So I'm not going to go through those. Asymptotes are not part of the graph. They're shown with dashed lines so that I can see characteristics of the graph, but they're not actually part of the function. So what I want you to work on is the questions 1 to 3 before I go into the next part. It's important that those get done first. So what I had you do is I had you work on questions 1 to 3 with regards to, there we go, with understanding asymptotes, vertical and horizontal asymptotes. And within questions 1 to 3, what we were looking at was for patterns. Is there a way that I can look at the equations and determine the vertical asymptote and the horizontal asymptote without having to graph it? How do I determine the vertical asymptote? What do I need to look at?
The zeros?
The zeros of what part, though? The numerator or the denominator?
Denominator.
The denominator. So the vertical asymptotes I will get by finding the zeros of the denominator, because that's when the graph is undefined. Okay? So the equation will be x equals that zero value of the denominator. Now, if there are no common factors to the numerator and the denominator, we can determine the horizontal asymptotes based on one of 3 patterns. And the 3 patterns have to do with whether or not the degree of the top compared to the degree of the bottom. So if the degree of the numerator is less than the denominator, the horizontal asymptote will always be the x-axis. So when the numerator is less than the denominator, when the numerator is greater than the denominator, I don't have a horizontal asymptote. That's when I'm in that no man's land. So for example, if we go back to these questions, so in part 1, that again, the degree of the top is less than the degree of the bottom. There's my horizontal asymptote. I'm going to skip part 2. Part 3, the degree of the top was bigger than the degree of the bottom. No horizontal asymptote. I have a space. Then when the degrees are equal, such as in part 2, what I look at is I look at leading coefficients. There's my leading coefficient 2. Leading coefficient is 1. 2 divided by 1 gives me 2. There's my horizontal asymptote. So we're drawing from patterns, and in questions 1 and 2, those were the patterns that developed. If I look at the degree of the top of the numerator, and I compare it to the degree of the bottom, that will tell me horizontal asymptotes. So if we look at class example number 2, it says algebraically determine the equations of the asymptotes of the graph of the following function. Verify using a graphing calculator. So if we start off with our vertical asymptotes, what I look at is I look at this function 2x squared minus x minus 3. And what I want to do is I want to find the zeros of that function, or the zeros of that equation. So I need to factor this. In order to determine whether or not it's factored, what I want to do is, can I answer the question, can I find 2 numbers that when I multiply them together I get -6, and when I add them together I get -1? Can you give me 2 such numbers? They multiply to -6 and add to -1. -3 and 2. So because the numbers exist, it means I can factor this. So then when I look at factoring it, because I have a coefficient in front of 2, I can either use that method of decomposition, or I can use inspection because I have prime numbers here. The only way that I'm going to get 2x squared is to take 2x and multiply it by x. And the only way that I'm going to get a 3 is to multiply 3 by 1. I just need to figure out where do I put the 3 and where do I put the 1. If I put the 3 here and the 1 there, I'm going to get a 2 and a 3, and the difference would be 1. Make this a negative 3 and a positive 1. So if I have a factor of 2x minus 3, what's the 0 going to be?
3 halves.
So then my asymptote would be that x equals 3 halves. And if I have x plus 1, what's the 0 going to be?
Negative 1.
So then my asymptote is that x equals negative 1. So that will give me my 2 vertical asymptotes. For my horizontal, I look at the degree of the numerator and the degree of the denominator. What is the degree of the numerator? 2. What's the degree of the denominator? 2. So they're equal to each other. When they are equal to each other, the horizontal asymptote becomes the leading coefficient of the numerator divided by the leading coefficient of the denominator. So what's the leading coefficient of the numerator, of the top? Pardon? 1. And what's the leading coefficient of the bottom? 2. So then my horizontal asymptote would be that y equals 1/2. So if I grab my calculator and bracket x squared minus, is it minus x or plus x? Sorry. Plus x. Plus x minus 6 divided by 2x squared. Oh, sorry, I have to put a bracket there. Okay, 2x squared minus x minus 3. So when I look at this graph, it's not really giving me a lot simply because my window settings are too big. If I change this, and let's say I went to a zoom decimal, if you notice right here, the graph is actually going above the x-axis. So it's not something that you could see before, but you can see now. And if I look at my table of values, sorry, let's put it on auto. When x equals -1, there's my error. And if I look at my values, these numbers here are getting smaller and smaller. As x gets larger, my values get smaller. And then I'm at between 2 and 1, I go from 0 to -1. So if I was to put a table set on, if I was to put it on ask, and go back to my table, I have when x equals 0, when x equals 1 was -1, and when x equaled 2, I was at 0. And then when x equaled 3, I was at this 0.04. If I put in 2.5,
I think we have a different graph, yeah, than you do.
do we?
Yeah.
X squared plus, okay, 2x squared, did I put a plus somewhere? We shouldn't have different graphs. Do you have graphs on yours?
Yeah, they're different.
Okay, so now that we have the right graph, because the graph, the parts that I want to see are centralized in this area, if I did do a zoom in or a zoom decimal to start off with and kind of focus in, then it's easier to see. I've got this horizontal asymptote or this horizontal space that's coming in through here and the two verticals that are coming in at -1 and at 1.5. And then I can see that this asymptote is kind of coming in as the value of x gets larger. So if I was to go to my table and take larger values of x, so 1, 2, 3, 4, 5, 6, you can see that the number is getting to be 0.5 and then 0.56, 0.57, but it's not something's going wrong there. Are you getting the same values? When x equals 3, it equals 1/2. Actually even showing a horizontal asymptote then, which doesn't fit the rule.